Hello, everyone. My name is James Swanke, and in today's presentation, we will be discussing testing of a high-speed surface permanent magnet machine for electrified aircraft propulsion. In today's presentation, we'll be discussing, I'll first give a brief introduction to myself and the project that I'm working on. I'll then go into the scope of the project and some of the challenges associated to it. The fourth item we'll go into is the technical approach we use to meet these challenges, as well as the HPK equipment that we used. And before closing, we'll just go through a brief summary of the work we've done. So to get started, my name is James Swanke. I'm a PhD student at the University of Wisconsin-Madison. More specifically, I'm a researcher in the Wisconsin Electric Machines and Power Electronics Consortium, or also known as WEMPEC. We do research related to electric machines and drives topics and related topics. Personally, I fall more on the machine side of what we do in research. I am a part of the OSU-led project supported by the NASA University Leadership Initiative, or ULI, where we focus on topics, focus on the technical challenges associated with aircraft electric propulsion. Many system-level studies show that there are potential benefits in terms of emissions and fuel burn by switching to electrified aircraft concepts. But a lot of there are many technical challenges associated to this that need to be fleshed out. I think it's also important for me to acknowledge the universities that we're working with. As I mentioned before, this project is being led by the Ohio State University. We're also doing this in collaboration with the University of Maryland, North Carolina A&T, and Georgia Tech. Our main project objective is to develop a power-dense megawatt scale integrated motor drive. For those of you who don't know what that is, I've included a concept drawing in the bottom left-hand corner. What this consists of is your typical electrical machine in the center, which is your stator and your rotor. And what we want to do is integrate the power electronics on the outside of the machine stator, or integrate it into the housing. Doing so, you have potential power density benefits in terms of combining cooling structures and just mechanical structures, as well as potential efficiency benefits by eliminating cables. As additional level of an additional thing we're looking to do is to make the power electronics modular, which would have certain benefits in terms of voltage levels of the machine, as well as potential, maybe later fault tolerance benefits. So where UW falls in this is that we're leading the motor design and development effort. I want to acknowledge the rest of the team. This team is being led by Professor Johns and Professor Blent, with grad students Jiraj Baba and Housing and myself working together to work on these motor challenges. So ultimately, we want to get to this final 1 megawatt machine, and that's really challenging to do. And so as an intermediate effort, what we've done is built a high-speed 200 kilowatt demonstrator machine designed and built to assess these final design risks. And one of these risks is to validate our machine electromagnetic models to make sure that we're estimating the correct losses and the correct performance. But this also extends into other things like the manufacturability of the machine design, perhaps the mechanical, since we're looking to push the machine speed. I don't think I mentioned it before, but we're shooting to get a 20,000 RPM, 200 kilowatt design. Ultimately, what we want to take away from this demonstrator is we want to integrate our findings into our final megawatt integrated motor drive design. To give you an idea of what goes into something like this, I've just shown just the electromagnetic components of the motor located at the bottom. Here on the outside, you'll see our stator. It consists of a stator core, which is just laminated steel, and stator windings, which are color-coded based on their phase. So this is a 3-phase machine with ABC phase windings. If we shift our attention to the inside, we'll notice that we have magnets mounted on a rotor core. So this is a surface permanent magnet machine topology. These magnets are then contained by a carbon fiber sleeve. We're going with a 12-pole design with a ring magnet. But to give you an idea of what the entire electromagnetic assembly looks like, I've included also a full drawing on the side here. You'll see that we're using a concentrated winding, so each stator tooth is wound so you don't have any overlap in your end windings. We also chose materials that would help the machine achieve the highest possible efficiency as well as power density. And to do so, we're going with a Litz wire for our turns. We're using cobalt iron laminations, really because they have great high frequency loss performance and high magnetic saturation. And then we're going segmented samarium cobalt magnets, which really have good high temperature performance ability. So we chose all these materials in order to meet the ultimate end of power density and efficiency. An additional thing that we included in our demonstrator is we broke it into 6 3-phase modules. And this would be similar to what we're going to do in the final 1 megawatt machine. It also gives us some flexibility in terms of how we want to connect the machine as we do our test. What this would look like and what this looks like now in our final machine is shown in the picture on the right-hand side of your screen, where I've highlighted one of these module terminal blocks where, so this one terminal block has a ABC and a neutral associated to it, and you can count that there are 6 of these located on the back of our machine. To give you an idea of what this looks schematically and how we're going to connect in terms of our test, I've also included this on the right-hand side here. On the bottom of your screen, you'll see those 6 3-phase modules located at the bottom. We've grouped these separate into 2 groups. In each of these groups is going to be driven by its own 100 kilowatt 3-phase silicon carbide inverter. We're connecting all of these, each of these groups in parallel in order to meet our 600 volt DC bus requirement. And one really just, this is starting to tie into some of these challenges we're going through, is that, going with this type of configuration really increases the number of electrical measurements we need to take in terms of really assessing our machine's performance. And this kind of takes me to the next point, where what we really want to do is assess this machine. So we've heavily instrumented it in order to get as much information as possible about the motor itself, so we can take that information into the final megawatt design. So what we've done is we've inserted over 40 thermocouples in the machine, and this is located in the machine windings, in the housing, and at various places in the cooling loop. And an IR thermal sensor, which is trained on our rotor, so we can get an idea of what temperature the magnets and rotor, the magnets and the carbon fiber sleeve are at as we operate. Obviously, we're going to be taking torque and speed measurements. We have 3 accelerometers located on our machine in order to assess vibration for the final design, but as well as also to alarm off in case something does happen during our testing. We've also included 2 coolant and pressure flow sensors, so we can evaluate our liquid cooling system. And lastly, just to reiterate the point I made previously, we have 12 current sensors, which we're monitoring both the inverter currents and one of the phase modules, one of the machine phase modules. To kind of conclude this slide, or wrap up this slide, I've shown a picture of what our test setup looks like and what we're going through right now at the University of Wisconsin. On the left-hand side of this picture, you'll see our demonstrator motor, which is connected to a dyne, a UW. On the other side of this picture, you'll see our inverter enclosure, which contains our 2 silicon carbide drives. And in between, we have a motor connection terminal box, which is connecting our 6 3-phase modules to our 2 silicon carbide inverters. Taking in all this information, all the different data from the different sensors we have in the system, we have our data acquisition system located on the side here. And this really takes us into the next part of the presentation, where we have this challenge where we have all this data, though it's really difficult for us to be able to manage it and to do that effectively using perhaps some of the conventional approaches you would in lab experiments. So as I said before, the modular motor test configuration and multi-physics sensor pose demanding data acquisition instrumentation requirements. And what we found is that the Genesis Rack and the Quantimax modules really cover all of our test needs. So we have a really simple, one-stop shop solution for all of our sensor needs. What this also does is it gives us synchronization across many channels. And this is especially important for motor testing, where synchronization is really required in order to assess a machine's efficiency. And then I think I did allude to this previously, but this setup allows us to be compatible with many different types of sensors, since we're really covering a wide range of different variables we're trying to monitor. In the center of your screen is a picture of the data acquisition cabinet itself. And just to give you an idea of what we have and what we're using, we first on the top have a QuantumX backplane, which has 3 Type K thermocouple modules located here, and these modules are collecting all the data from our thermocouples. If you shift your attention to the bottom, we have our Genesis rack, which has first cards for our voltage and current measurements. So this is measurements coming from our DC bus, from our inverter outputs, as well as from the motor modules themselves. On the bottom, we have a universal input card, which just allows us to take in multiple different types of sensor types. We're using this to take accelerometer measurements, our flow pressure measurements, and our IR sensor measurement. And last, we're able to connect our torque and speed sensors, as well as our flow sensor outputs to these DB connectors located on the front of the rack. So we're able to take all of our sensors to one place. I guess that's the point. And well, that's really good. Really the other side of this is on the software side, which leads us to the HPK perception software benefits. The first thing that we really liked about this is that it really simplified our motor test setup, and we were able to do this by using their eDrive software. It was pretty much just selecting our components. We told the system how we connected our machine. We have our 2-drive system with a single DC bus, so we were able to easily specify different components we're using, and that was really a breeze. Additionally, the perception software really gave us it's really easy to take the synchronous data recording for both viewing while you're testing, but as well as later with the post-processing. It's nice that you have one recording that contains the data, that contains all of your experiment data, and you don't have to track down different things. So it really makes things easy for organizing. Another important aspect of all of this is the ability for us to enunciate alarms in perception if variables reach undesirable operating points. And this really goes back to things like the accelerometers and the winding temperature sensors, which we really want to make sure that those are within acceptable levels so that we can keep the machine healthy, and we can make sure that we are able to test the machine to its fullest ability. Just to give an idea of what this looks like in perception, I've included a couple of screenshots of our workspace. The top screenshot shows waveforms from our inverters. So it's a little bit faint to see, but the top waveforms refer to our inverter 1 currents. So this is 3 current measurements. And the bottom one refers to inverter 2 currents, which is another 3 current measurements. So we're able to see that, as well as the other sensor types. We're also able to dedicated a screen to monitoring our machine winding temperatures. And this is what we're really looking at to make sure that we're not pushing the machine too hard and exceeding its thermal limits. So just to summarize what we're doing, our challenges and our solutions all link to each other, and I kind of follow a certain order. So I'm gonna go from challenges to solutions and back to challenges. But our primary challenge is what we want to do is we want to reduce the technical risk for a megawatt integrated motor drive for electrically propelled aircraft. And the way that we're going to do this, our solution, is to develop and test a low power demonstrator to assess our tire risks in preparation for the final zone. So now that we've decided that we want to go with this lower power demonstrator, we need to be able to thoroughly assess the machine's empirical performance characteristics in order to feed that back into the final design. And the way that we do this is that we instrument this gets to the solution. The way we do this is we instrument the machine to measure as many electrical, mechanical, and thermal variables as possible. And now that we have all this data, we have a new challenge where we need to record, monitor, and evaluate many channels of machine data to evaluate and verify our machine performance And this takes us to our ultimate solution of using the Genesis rack and the QuantumX modules, as well as the perception software, which really is which meets this ultimate challenge of trying to manage all this data. So just to wrap up and to summarize the benefits, the first benefits associated with the first challenge is solution. So it's crucial for us to accurately measure and evaluate the performance of the demonstrator machine in order to quantify the technical risks and, where necessary, identify fixes to overcome them. The second benefit is to take the results of our demonstrator work and feed it directly into our megawatt class machine and power converter. So we want to take the results of our 200 kilowatt machine and inform the final 1 megawatt machine design. And finally, the last benefit, and this is more related to the HPK equipment, is that the use of the Genesis rack, the QuantumX modules, and the perception software provided us with a complete instrumentation solution to view, monitor, and evaluate extensive data for multiple types of sensors. So with that, I want to say thank you for your attention. I also want to say thank you to Krista Tweed and Mitch Marks from HPK for all of their support in terms of our testing at University of Wisconsin. We've had many questions and they've always been able to help us. So with that, I would like to take your questions. So thank you.